welcome to our last spring of 2023 Quantum Thursdays. And we are delighted. I would sometimes say they saved the best for last. But we've had some really wonderful presentations this spring, but we're really delighted to have Michael DeMarco here with us. And he's got a phenomenal background and story to tell you. And we are also joined by his mentor, Mark Rittner from IBM. And I'm going to turn the floor over to them. So we will, Michael will do his presentation for about 45 minutes, and then the last 15 minutes we'll leave as usual for questions. And post your questions in the chat as we go along, and we'll go. Mark?
Thank you, Raymond. Well, good afternoon. I'm the chair of Physical Sciences Council at IBM Research, and I'm also leader of the cross-cutting co-design or EXCITE team in the C2QA Center. And Michael was the first postdoc hired in the C2QA Center, and he's had a great impact on cross-cutting co-design work. He did his undergraduate studies at Rice University in Houston, where he studied physics and mathematics. He then obtained a master's degree in theoretical physics from the University of Cambridge, and then came to MIT to begin his PhD work. After 4 years at MIT, he left the program to found a startup, which he grew to acquisition and returned to MIT in 2020. His PhD work was on Chern-Simons field theory on a lattice, showing exactly soluble formulations to describe topological phases of solid-state phenomena, like conductance of fractional quantum Hall systems. He obtained his PhD in 2022 and is now at Brookhaven National Laboratory with a visiting position at MIT, where Ike Chuang is his mentor, and Ike is also the co-lead of the EXCITE team. In the C2QA Center, he has helped greatly in the EXCITE projects, leading many of them that have resulted in 2 highly collaborative cross-organizational and multidisciplinary analyses of multinode and heterogeneous quantum computing systems. Personally, I wish to thank Michael on behalf of the EXCITE team for being an energetic, creative, and collaborative member and leader in the team. You have advanced the co-design mission of the C2QA Center and are helping develop the science of quantum co-design. So thank you, Michael, and I'll now turn it over to you.
Thanks, Mark. I really appreciate that. Hi, everybody. It's great to be here with you today. I'm going to start sharing my screen here. And I was instructed to tell you a little bit about me at the beginning of this. So I've got maybe 7 minutes. We should be done by 12:10. And in anything like this, I think it's tempting to be self-indulgent. So I'll try to give you a quick rundown of how I got here. And the message to leave with it is how hard it was to get to a career in physics, how much fun it was along the way, and how the people that I got to work with really made that whole difference. And just as a disclaimer here, I did not know Mark was introducing me when I put this together. So he's part of the story, and it was just totally honest, because I only found out like maybe half an hour ago that he'll be here too. So just kind of where I came from. So I grew up in Texas, in Dallas, Texas. I went to Rice University, and I wasn't like planning a career in physics. I wasn't very good at school. I was kind of in trouble a lot. I don't know if anybody on this call has a similar background. But I took physics my last year of high school because you have to in Texas. And within like 6 weeks, I was like, oh my goodness, this is what I've been looking for. So I scrambled, I got to college. I was super behind. Everybody else had taken like multivariable calculus. I was teaching myself calculus out of the book just to catch up in classes. My first research project, I convinced some particle experimentalists to let me calibrate circuit boards. And here's actually a picture of one of the boards. These are actually used at Brookhaven on the STAR experiment, which I've never seen in person, other than driving by it. But I was sitting in this really dark, somehow always cold room, even in Houston, Texas, calibrating these circuit boards. I then jumped around research projects. I worked in biophysics for a while. I settled in atomic physics, where finally I kind of got to a place where I liked what I was doing. I was working on the theory for these new phases of matter. And it was a sort of long, winding road to get there, but I really enjoyed it by the end. And one of the things I want to emphasize on this, I know we have sort of a mostly undergraduate audience, is just how much like good friends were really important to get there. So in the bottom picture here, this is actually the physics class of Rice. I still know all of these people. I still talk to them on a fairly regular basis. One of them is here at MIT, this guy, Josue Lopez, and is still a very close friend of mine. And it was like, because we were up all night, so many nights in a row, working together, trying to get through the undergraduate degree there. I worked with a lot of friends teaching like math and science in summer schools over the summer. Sort of these experiences were really core to actually making it through the technical parts of the degree, and really core to what I was able to do after that. So from that, I went to Cambridge, which was an amazing place. I got a scholarship to go there. This was just wild to me. So like in this top left picture, that is the library where Newton wrote the Principia, and you just get to go there. And if you look really closely, you see a guy who has no idea what's going on. One of my biggest memories in Cambridge was they had these dinners and you just go to them as a student. Like you go to these very fancy dinners. It's just what everybody does. And I did not know how the forks and knives worked. I just was used to like one fork, one knife that you get out of like the fast food. So I remember watching very carefully to understand like, just how all manners worked and catching up as fast as I could. It was also this amazing place because the physics there was wonderful. I got to learn all this string theory, all this quantum field theory, and it was something I was really curious about. I think as a physicist at the time, if you grew up watching Nova, like you want to be a string theorist, I was definitely one of those. And so I got there, I took a bunch of string theory and I realized that string theory seemed like its best days were behind it. It was never going to compare it to experiment. It would never tell us about sort of the world that we lived in. It was a beautiful mathematical formulation, but I wanted to have something that was closer to reality. So I went to condensed matter theory. And this was actually a really tricky decision because it meant staying in Cambridge for a PhD or coming to MIT. And so, choosing continents, choosing fields, all with relatively little information. Ultimately, I decided that going someplace where things were really new and really fast and developing very quickly was the better call. So I came to MIT, which is actually where I am today. My work there was on a simple question, which is, can you simulate the universe, in particular the standard model? So it's a lovely pitch. Until our work, the answer was pretty much no. The standard model has an asymmetry in it called chirality. And we didn't think that you could put a chiral theory on a lattice. My work was, well, there are chiral phases of matter. We create them in labs all the time. And they have similar physics. Could we use that intuition and some of that formalism to actually be able to simulate a chiral field theory on a lattice and then at least open one avenue towards simulating the full standard model? This took 7 years to get. We wrote a bunch of papers, slowly getting there, and we finally got one chiral field theory just before I finished my PhD. That sort of was my thesis project, and it's something we're super proud of. The ramifications of that going on are still being understood, and that's something that I think is one of the prouder parts of my career, except for what came next. But before that, let me get to an interlude, which is I was at MIT for 7 years during my PhD, but a year of that, I actually left and created a startup. I've been working on a side project on weekends with a bunch of friends on actually for how people running for school board can run smart campaigns. I was used to all of the big politics. I think we see that all the time and the nastiness in the news. I wanted to work on like school board elections, municipal elections. So me and a bunch of friends got together. We had built something, it started to take off. We incorporated an LLC. We all moved into the same disgusting apartment in retrospect. In Cambridge, and just worked and worked and worked and built this thing. And we had this software I'm so proud of. It went out. It's to help school board candidates go door to door canvassing. And we launched that software. And here's the important part, on March the 1st, 2020. So door to door and March the 1st, 2020 don't mix because the pandemic hit like 3 days later. And everything we had built just didn't matter anymore. My role was sort of holding the team together. It was actually our CTO, Lisa Vo here, who had the brilliant idea of we'll switch to phones. We retooled everything. We got it back to growth. We had people finding us on Google, signing up, paying us money to use the service, which is a great sign. But sort of took a look at things and said, okay, this moment has passed. let's go back to school. We'll find somebody to buy it and carry it on. We did, and the startup was acquired. So that was wonderful. I came back to MIT, finished my PhD with that big problem, simulating a chiral field theory on a lattice. And then I found another problem, which is I had sort of solved my problem. This is something I worked on for 7 years. I wanted to go on to do other things, and I wanted them to be impactful. And I kind of had this problem, which is all my work was still very theoretical. I didn't think it would affect anybody like back home in Texas in my lifetime or my grandkids' lifetime. So I knew I wanted to move towards quantum. And I was working on some policy things at the time. I went to go interview sort of a great person to talk about quantum policy, Isaac Chuang. I think a lot of us have read his book. I went there to interview him for a paper I was writing. It turns out he was interviewing me. At the time, at the end of that, we started talking about this job. He said, come work on co-design at C2QA. That was, a massive jump for me, just jumping into the fray. And it was one of the best decisions I've ever made. The most important part of it was the people I got to work with. So Ike is here at the top left. Mark is right next to him, who just introduced me. They have led this team. It's been just phenomenal getting to spend time with them. They've taught me so much about physics, about doing science, about working with other people and leading teams, asking really important technical questions and understanding the big strategy of things. The people I've gotten to work with in the center, there are others up there, Kim, who has been leading the series, Andrew Houck, Jim Masevich, Dave Mackay. There's a whole big team who I don't have enough pictures of all of our meetings to get us together. There's something like, I think 40 or 50 people who have been through the Excite team. I'll get to tell you about some of them later today. But this has just been a fantastic experience. And I don't think I could possibly say enough about how much the wonderful people here have taught me and how great they've been to work with. So this has really been my professional home. And hopefully you have a sense of, I searched for a long time, came to this professional home, and it's just been lovely since. So on this next slide, I have a little summary. If you're an undergraduate, you're looking down this, what I wish I had known is like, it is a long, hard road for sure. It's a really fun road, and you get to work with amazing people. And those people are the ones who will teach you so much and who kind of make it worth it. So if you're looking at this and you're thinking, hey, I might be thinking the same thing, feel free to drop me an email. It's right there on the screen. I'm pointing to my screen because it's over there. But with that, if there's no questions, we can jump right into the actual technical side. Does that sound good? Okay. Great. And I think we're right on time. So this is a paper called Architectures for Multinode Quantum Computing. It grew out of the Architectures for Quantum to Interconnects team, the ARQUIN team in C2QA. You can see it's a massive team. I am not today going to get to tell you about every single person's contribution. That would be all day. But I will get to tell you about some of them and some of the big ones and how this team came together to talk about making distributed quantum computing a reality. So we're going to start sort of, what do I mean by multi-node or distributed quantum computing? What are the components to go into it? What's the system analysis that we need to think about? How do we get towards multi-node quantum computing, and sort of offer some waxing thoughts about the future directions for multi-node QC. So what do I mean by this? There's an idea that's repeatedly showing up in the field about using a bunch of smaller devices that are somehow networked together and to make a large quantum computer. The IBM roadmap is here front and center. There's a lovely Scientific American article by a handful of people in C2QA. This goes back to Chris Monroe's group. Michael Hatridge has some wonderful work actually making sort of modularized computers that can be pulled apart. The basic idea here is that making a big quantum computer is hard, sort of for a different reason in each of the different platforms, but it's much easier to make smaller devices and stitch them together. That's notably also why classical computers work this way. It's why you have many cores, or I'm talking to you on a MacBook with many cores inside of it. Today, I'm going to focus almost entirely on the case of superconducting systems, mostly to think about microwave-to-optical transduction in that. So what do I mean by that? Well, here's two dilution refrigerators. And in the near term, like literally in IBM's roadmap, we'll be looking at a few different chips in a single refrigerator with microwave connections between them. So this is, just chips wired together. They're inside the same dilution refrigerator, and they have quick communication that's pretty good between them. But longer term, as these things grow, we run into a problem, which is one, you just run out of room in a dilution refrigerator. We're going to need a dilution refrigerator the size of like a ship before too long, who knows? We're going to need to be able to service these systems, right? You don't want to have, if you're offering quantum computing as a service, you don't want to have to take down your entire service to do maintenance on a fridge. So we'd really like to be able to somehow network these together, like one chip in one refrigerator, one chip in another, and connect them together. You can think of this as sort of like the beginning of networked quantum computing, but I will not today be thinking about repeaters. Now, this opens up a problem, which is if you want to go between two fridges, the links probably need to be warm in order for this to really be a scalable architecture. Now, warm links cannot hold microwave information. Just at room temperature, if you have a wire, there's probably about 1,000 microwave photons bouncing around in there. But all of our superconducting qubits are naturally operating in the microwave regime. So somehow I need to take a superconducting device that operates in the microwave regime, transduce that information to the optical regime, which can go down a wire, and go back down to the microwave regime. The way to do this, the word for that is transduction. And the bad news about it is transduction is a nonlinear process. And you sort of need to be able to take something that's just like a 5 gigahertz signal and turn it to, say 1 micron in that order. When you do that, you're going to lose a lot of your signal. Okay? And in fact, it still shocks me that we're able to do this, but you can lose about 30 decibels, which is about 1,000 times or 100 times noisier and 10 or 100 to 1,000 times slower than local operations. And I remember most when I was starting this, I was talking to Hong Tang, who's one of the authors on the paper, and is building these experiments. They're really heroic level experiments. He said, you're going to send 1,000 photons down the wire, and you're going to lose 999 of them. Okay? And we want to do computing in that regime. So this is sort of where we were. This is me. I am C3PO in this, and Hong Tang and Ike Chuang were saying, we're going to do this anyways. We'll find a way to make this work. So you can see me sort of circling a question here. Let me sharpen this. We have nodes. We want to do internode links between them. Those are a severe impediment to actually making a multi-node system work. Okay? And it's not just that they're noisy, it's that there's going to be some like funky trade-offs that we need to think through. So we need to both understand that if you have an internode link, you could actually do what's called circuit cutting to it, which is where you just stitch it back together with post-processing using classical computing. That's going to have some cost. There's some lovely circuit cutting work. I think you heard from Wei Tang earlier this semester, who's one of the experts on it. I'll review a little bit of that later. But also, chances are, and this is the same trade-off that's roughly true in classical computing, you can often get rid of internode communication in exchange for a lot of local computation. Given how noisy, what's worth it? We need to sort of answer these balance questions. And only once we understand these three balances, between internode gates, between local gates, between circuit cutting, can we really answer the question, what sort of performance do we need from our internode gate to make a multi-node system worth building? And just to think about what's been done on this already, there's a lot of really lovely visions of high-level quantum network. There's this Steffi Werner wrote this fantastic paper of this blue figure in 2018, thinking about sort of what capabilities you develop in what order as you develop these networks. There's great system performance models of how a network can operate at the abstract level. Stefan Krasinov has one of my favorites here, but there's a bunch of others. There's low-level models of the hardware going into each of this. We'll use a lot from the Yale group, that's the NARLA PRX. What is missing in this is actually a systems analysis from the bottom to the top. Given hardware performance, given how networks work, given what I want my network to accomplish, what performance can I achieve? What do we need to get to? And that's actually a place where our team that Mark leads and C2QA is exactly positioned to answer. Our job is to think in between experiment and theory, to do the systems analysis, to set the roadmap for what hardware needs to do, what algorithms need to get used to in terms of performance, and how do we sort of bridge the gap between these two? And strategically in this, there's a good metaphor for this, which is this old story. I'm sure everybody's heard it, about the six blind men who are describing the elephant. It's a story that showed up like 4,000 years ago in sort of the Indian subcontinent, and they went everywhere. So this is a woodcut from Japan in the 17th century. It's sort of all over, I think more in East Asia, but also obviously made it through Europe over the 4,000 years of its existence as a story. I think of each of these examples as like the one of the blind men being like, I'm touching the side of the elephant and it feels like a wall. I'm touching the trunk of the elephant, it feels like a snake. And what they're all going to do is they're going to go tell a seventh blind man, that's us, who needs to take each of their descriptions and understand what an elephant actually is. And the reason everybody's blind is nobody's built a working quantum network yet that works at the performance that actually can do real computing. So we have to be able to take other people's individual simulations, stitch them in together into some overarching simulation of what this network can do, what a multi-node computer can do, and do it without being able to stress test our ideas on actual hardware, because a multi-node system has yet to exist. So that's my sort of big question. I know that we can take questions at the end, but if you have a question right now, this would be a good time, because this is sort of the setup, and now we're going to jump right into the details.
You can raise your hand and I'll just unmute if you want to.
Cool. All right. What do you say we go on, Ray?
Yeah, I was going to ask you which section of the elephant are you holding on to?
Oh, so that's the thing is right. We're the one that all the blind men have to go talk to,
Okay.
so we don't even get to see it. we're the seventh blind man who takes the 6 reports and is like, this is what an elephant looks like.
Draw an elephant.
Exactly.
Good. Yeah. No.
So,
okay. Go ahead. Let's.
Excellent.
Okay. Good.
Great. So let me start on the first question. Given current and planned hardware,
There was a
systems,
question. There was
great.
Eric.
Hey, Eric.
Eric, you want to unmute and ask it?
Oh, sure, yeah. So I mean, this need for transduction is assuming computing is done with superconducting qubits working at the microwaves. But what if photonic quantum computing working in the near infrared turns out to be the way to go?
Yeah, so then you can avoid transduction. At the end of this presentation, I'll loop back and sort of offer some thoughts on how this same analysis should be repeated in other platforms. Let's say you want to have a neutral atom platform, right? There you can imagine modules which either pass atoms back and forth using tweezer arrays, or use some sort of optical communication as well, which is nice because you don't have to do transduction. Usually across all these models, it's sort of universally true that your link will be weaker than computation inside your node. Understanding the balance between internode and local computation still becomes very important. It will be more favorable in some other systems, and I'll be able to offer some thoughts on that and some teasers of some more excite work coming out in the future.
Cool, thanks.
You bet. Cool. So this is where we're going to start. Here, just what can we expect from our internode gates? Okay. And this is where I'm going to go through all the components, right? These are the 6 stories of the elephant from the blind men, and sort of talk through each bit of it, how we simulate it. I'm a little bit behind schedule, so I'm going to go slightly quick through this. If you have questions, if it's a long question, save it to the end. If you have a quick one, you're like, wait a second, Michael, you said something wrong, or you just forgot something, or there's something that would be integral to your understanding, go ahead and pop it up. And you can just talk over me if you need to, or raise your hand. So something to think about in these systems. We're going to need to be thinking about heralded entanglement generation. We're going to think about entanglement distillation, and we're going to talk about remote gate execution. I'll go through each of those. I just want to think about the complexity of this. This dumbest thing I could do is something like 4 rounds of distillation. That sort of, if you do something like that, you're going to need to do something like 20 qubits per link just to simulate one of these systems. Okay, so a 10 qubit quantum computer with 1 link in it would be like simulating 30 qubits. That's an insane amount of computational power that is clearly the wrong thing to do. We need to find some sort of way of abstracting away the details of quantum links to make sense of how the hardware works without getting into exponential computing costs. Okay? Moreover, right, we not only just need to understand how these resources interact, but how we optimize their actual operation. That's this story about how to trade off local internode and circuit cutting gates. And lastly, we need to build this with some hardware uncertainty. We don't want to just analyze superconducting systems. Eric, to your question, we want to be able to sort of think about how to analyze all multi-node systems in some coherent framework. I'm doing everything today for superconducting systems. I will come back with, again, some teasers about ways to do this for other systems. So in terms of making this simpler, right, that's the thing we need to do. We need to abstract away the behavior of this link. In classical computer science, this has been well established. What we want to do is divide our system up into layers with specified interfaces. If there's any classical computing folks on the call, you'll recognize some terminology from the OSI model that is intentional. The basic idea here is that I don't just sort of execute some internode operation in a quantum system. What I do is actually I generate entanglement, I distill entanglement, and then I do one local gate in between them. And then I can think about higher levels from that. To build an architecture to abstract away this, all we do is we take a layer for each of these fundamental operations. And each layer here will be a set of ideas, a theoretical framework that for quantitatively treating the behavior of this layer, and also a module in our simulation that numerically outputs whatever we think the metric should be for each layer. And by doing this one at a time, I never face some sort of 30 qubit, 40 qubit system. In fact, I just see sort of a handful of qubits at a time, and I can really cut down on this exponential density matrix simulation cost. It's also, and this is important, a way for structuring our people. There's a huge number of authors on this paper. It's a sprawling thing because there are so many different parts that go into a multi-node computing system. So these layers actually organize us. Yale did a lot of the physical layer simulations. Princeton and UMass Amherst taught us about how to move. So physical layer produces entanglement, how to move entanglement into actual superconducting hardware. Once it's there, it needs to be distilled. Virginia Tech did those simulations. Let me come back to PNNL, Pacific Northwest National Lab. They did a ton. IBM thought about at the top layer, if you have some sort of modular system, what sort of compilation do we need to think about over that? Brookhaven and MIT, that's myself and Ike Chuang, we designed this architecture and pulled the team together. And Pacific Northwest National Lab, coming back to them, they actually designed and built the simulation pipeline that connects all of these pieces together. So this was sort of a massive group effort, and the architecture not only simplified our computation, but simplified our sort of team dynamics because we needed to work together in this manner. So moving on through this, the first thing that we need to think about in this is how do we genuinely generate entanglement? And I apologize for this figure on the right. It's the strangest thing. If I save a PowerPoint, this figure gets really grainy. And I apparently resaved the PowerPoint this morning. In any case, if I'm losing 30 decibels of signal, that means I send 1,000 photons down a wire, I lose 999. You need to have some sort of heralded scheme to make sure that we can actually generate entanglement and know when we have, since we're going to fail 999 times out of 1,000. There's a bunch of different schemes out in the literature for this. I'm going to focus just on one today. We evaluated all of them, compared them, and chose one. The one that we're going to settle on here is here in the bottom. What I do is I have a qubit and I entangle it with a propagating microwave photon. Okay? And I do this in two sides. This microwave photon is a wire. It goes through a transduction hardware, a microwave-to-optical converter. And now here at the end, I interfere the optical photons in a way that erases the which path information. So here's a beam splitter, and then I detect them. Here's something very important is we're using what's called the Hongo-Mandel effect in quantum, which means that actually at these detectors, they will either both detect an optical photon or neither detect an optical photon if I've set my path links correctly. So when they both detect an optical photon, I know now that I have a successful generation of a pair here and here. If, for example, I lose a photon, which I do a lot of times, then I'll only get one click. Okay? Only one detector will herald. And so then I know that I was unsuccessful in actually generating entanglement. Now, something critical here is that I actually can choose how strongly to entangle my propagating microwave photon with my qubit. If you want to generate entanglement quickly between qubits, you should strongly entangle this guy with the microwave photon, which is then going to go over to the beam splitters. However, because I lose so many of these photons, that actually leads to a lot of errors. So there's some balance point, right? And one of the things I want to do now is sort of evaluate where that balance point is on how strongly to entangle this qubit with the microwave photon. But I'm not going to be able to do it alone. And this is where this layer picture becomes very increasingly important. Because I am also going to do something else. Once I've generated entanglement, I'm going to distill it. So let's say I have a bunch of entangled pairs that I'm going to create. I can then do some distillation operations, which consume many entangled pairs and give me fewer of them, but with higher fidelity, that's lower error rate. There's a bunch of different entanglement distillation protocols. The sort of foundational paper on this was written at IBM, and I highly recommend it. It's John Smolin and collaborators Charlie Bennett, I think David DiVincenzo, and Mark. I think there's one other, so please forgive me. But the basic idea here is we're going to take a bunch of noisy entangled pairs. We're going to get somewhat fewer of them. Now, because it takes me time to produce every entangled pair, this is actually a very similar trade-off to what I navigated in the previous slide. This is about fewer errors, but slower time. This is, again, fewer errors and slower time. And given my hardware, there's some sort of minimum infidelity that I'll get to based on the number of rounds of purification. Each one of these consumes, each single round halves the number of bell pairs, or takes twice as long to get to. So there's a second interacting trade-off here between the fidelity and the execution time of internode operations. And we're going to take these, we're going to put them into a fairly standard remote gate protocol. This is from Liang Zhang's paper in 2007. Basically, any sort of 2-qubit gate that you want to execute between these nodes, you can do using a single, any 2-qubit gate that you want to do, you can do using a single entangled bell pair. This gets more and more complicated for larger and larger gates. But the sort of ceiling that we want to know is just how long does it take and what's the error rate of an internode operation, okay? And how does that fall from and compare to local hardware costs? So I've sort of described each of the components. I'm going to briefly stitch them together here. And what we do is we simulate each of these in order and then staple sort of their outputs together, chain them together, to get just an estimate of what that error rate and the time to execute an internode operation is. So here's my infidelity or error rate. I want this to be low. Here's the gate time. I would like this to be short. These black lines are the lines traced out for, let's say I just do microwave-to-optical generation with no distillation. This is the line that's traced out as I more strongly entangle my qubits with the propagating microwave photons. As I do further and further rounds, I'll get less and less infidelity, but you notice it takes longer and longer. It's like I would like to be down in this corner, but instead you can just trace an arc of roughly equal distance. You're sort of picking your poison here. And we don't really know what's more important, infidelity or gate time. And we'll be able to see that later a little bit for some applications. I'll refer to this going forward as the Snoopy plot. This was named by Ike Chuang, so this kind of looks like a dog. So here's a snout, here's an ear, here's his tail. And so we're just going to keep remembering that going forward. So here's Snoopy, and he's actually looking at a Dolly 2 generated dog. And you can see that Snoopy's very worried about his future career prospects now that AI can just produce great looking Snoopies. So here's the pipeline that we're using. The specs are in the paper. If you're into sort of big honking simulations, I'm sort of glossing over this, but please talk to me afterwards, or we can get into it in the paper. Now let me actually go through and talk about the system analysis here. This is the 7th alignment. I sort of described the 6th one, each one seen one part of the elephant. Now we need to stitch this together. And I'm going to present 3 resource analyses here. First, I'm going to ask, in fact, let me just say this. How are the internode gates doing from hardware? This will be the gate algorithm performance plot. Then we'll get into how you should trade off the internode gates and local gates using a quantum roof-slide model. And finally, how internode gates should be traded off with circuit cutting using a quantum classical performance analysis. So starting here, what sort of internode gates can we achieve? What does this mean for system performance? What I do here is here's that same plot. Here's Snoopy. Snoopy lost his tail because at some point distillation just introduces more errors with noisy hardware. And this was a metric proposed by Dave Mackay from IBM. The idea is, let's just imagine a very simple system, 2 5-qubit nodes, 1 internode link. I'm going to ask, what is the quantum volume of this effective system? And the reason we chose this is it's sort of this nice single number that characterizes the effective Hilbert space traversed by a system. So it'll be something like, if there was no link here, the highest quantum volume you could get is 2 to the 5. And if there's a perfect internode link, the highest volume you can get is 2 to the 10, because there's 10 qubits. In between, we actually get sort of a scaled answer of how well this link is performing. So what do we do? What do we get? We can just evaluate this. Sam Stein did an amazing amount of big honking computer simulations to pull this off. Where do we get? Well, you can see here on the plot. Here's Snoopy. Here's the success reasons for quantum volume 2 to the 6, 2 to the 8, 2 to the 10. So we don't actually see any increase in the quantum volume for a multi-node system over that of a single node. This, I think, really underscores how hard it is to build these multi-node systems. But don't worry, it's not all doom and gloom. Quantum volume is sort of the hardest metric that you could look at. So we looked at a bunch of others. Ang Lee, Sam Stein, and Jim Ang had done a lot of work sort of on benchmarks that you can apply to these systems. They complemented also work from Tico Mesh and Margaret Martinosi and the Princeton group. Maybe quantum volume is the wrong thing we should look at. So we could look at something like preparing what's called a GHZ state, sort of a mini entangled state across the system, or the Bernstein-Vazirani algorithm. That's these two. We're able to successfully do that because of the distillation that we can navigate. On the other hand, more challenging things like an adder circuit, and I mean this sort of the quantum analog of the classical adder, or quantum Fourier transform. We're still sort of nowhere near several orders of magnitude away from being able to execute those sorts of algorithms. I'm going to rush through this a little bit to make sure we have time to get through sort of the fun part. But we also want to look at the balance between internode gates and local gates. And for that, we want to look at something called a roof-fly model. We're stealing a lot of this from classical communication, at least morally. So what I want to do is compute for a given circuit something called the computation communication ratio. It's a super simple metric. Just take a circuit, compile it, look at the number of local gates divided by the number of internode gates. And ideally, this should be equal to something which is like the machine's preferred computation communication ratio. So that's the CCR, this is the MCCR. And that's the internode gate time divided by the local gate time. I'd like these to be about equal. And there's a simple way to see that, which is if the internode gate time is very long, I'd rather have a lot of local gates. So I can put this on a plot. Here's the CCR on the x-axis. Here's the rate of execution of gates. Here's that balance point. All right, this is the MCCR. Whoops. And I can draw the bounds there and look at where algorithms fall. So if an algorithm is bound by this line, then it's bound to the computation bandwidth. It means that my local hardware cannot do operations quickly enough to execute the algorithm. On the other hand, if it's bound by this guy, then it's bound by communication. It means my communication in between nodes, my internode links, cannot execute quickly enough to keep up with the computational needs. What's important about this is, one, none of these are actually near the bounds or near the balance points, because it turns out our compilers are not well optimized for these multi-node systems. And two, as I do distillation means fewer errors in my internode links, but it also means a slower internode link gate time. And so what happens is this computation bound comes in from black to red to green. It gets tighter and tighter and tighter. Actually starts affecting how my computation needs to be performing. Remember, the computation wants to be at the MCCR, means it wants to get to this balance point. At this point, it needs to start adjusting for the long time it takes to do some of these internode gates. So this is a nice way to both answer, one, how should I trade off local computation versus internode computation? The answer is it's this MCCR. That's like the LIBOR rate. If anybody messes around with exchange rates, it's the ideal exchange rate. But two, it also allows us to abstract away all of the complications about, remember, this long simulation of internode links, and just tell the compiler how to trade off internode links versus local computation. So the last thing to get through here is, okay, I have a quantum link. Sometimes I can just cut that link and I can just do it classically. And what I do is I basically do tomography on either end. So I execute my circuit many times, do tomography on the result. There's a little bit of clever post-processing to do and stitch back together as if I had a quantum link. So this was proposed, and this analysis was performed by Dave Mackay at IBM. And sorry, the previous analysis, just to make sure I'm checking everybody, was done by Ang Lee at P&L. And then before that was sort of a huge team effort, but also led by us at P&L and others. And that's this quantum classical performance analysis. So just given the simplest thing, let's say I have K internode links and I want to do circuit cutting. How many circuit executions does that cost me? I'm using a fairly coarse estimate. There's definitely smarter things than this, but it's roughly 4 to the K. And I want to compare that to error mitigation, which is, again, running a circuit multiple times, but using that to correct errors. So IBM's a leader in this. And if you're familiar with literature, I'm thinking about probabilistic error cancellation, PEC. So here on the x-axis is the number of internode gates. Here's the circuit executions required. The red line is for circuit cutting. The dotted line is for error mitigation. As my errors get better, so as I do distillation, this dotted line moves down. So I need fewer and fewer circuit executions. What's important to remember is that, even with these terribly noisy quantum links, they're 100, 1,000 times noisier than your local computation. For something fairly simple like quantum volume 2 to the 8, that's like 40 internode gates. You can get away with hundreds, thousands, maybe millions of circuit executions if you're using a quantum link. If you're using circuit cutting, we're at 10 to the 25. That's just a completely unfeasible number. So the thing I'd like to sort of focus on here is, despite how noisy and slow these internode link gates are, we definitely need them, right? Circuit cutting won't cut it. And 2, the trade-offs with local gates are actually pretty steep. So usually MCCR is a fairly small number. So we'd actually still really need to look at these multi-node links. So just stepping back for a second, we've seen what performance we have from internode gates. We've seen how to trade that off with local gates for circuit cutting. Now I actually want to say, okay, well, how do we get good enough performance that these local gates that these multi-node systems really start seeing an advantage over their single node counterparts? And to do that, we'll actually need improvements across the stack. We need to think about better compilation. So how do we use internode resources more wisely at the top of the stack? We need to think about improved hardware or specialized memory for distillation. And lastly, we need to think about higher fidelity, faster entanglement generation. And one of the fun things about this sort of analysis that's so powerful is we can go through and look at specific proposed hardware advances and run our analysis up the stack and get an answer to how does the system perform. So this is where the paper accrued just a massive number of authors, because everybody could come through and say, hey, I have this hardware idea, I have this software idea, and we could run the numbers on it and try to get an understanding of what hardware, what software can actually go together to create a successful computation. I'm going to give just a few examples of this. We're getting towards the end of time. One of them is Hong Tang put together a sort of comprehensive plan of a series of research advances in the actual transduction of information from the microwave to the optical. If we were to pull that off, what sort of performance can we do? This both decreases the infidelity and increases the rate to the point where we can easily see improvements in quantum volume. We're sort of now in the success region. It actually dramatically reduces the computation bound and completely gets us to the point where circuit cutting is completely infeasible. It's sort of not even a comparison anymore. Okay, what if that doesn't work? There's experimental physics has a number of challenges. What if we just take current hardware and multiplex it? That actually both speeds up the computation and allows us to get to much lower infidelity, so much lower error rates. Simply because my distillation hardware, the chief error I pay there is waiting, so accumulating T1 and T2 errors while I'm waiting for more entanglement. Okay. And then we can kind of consider longer term ideas. If I could couple an ions to a superconducting qubit, ion provides really fast transduction. It's also a fantastic memory. Could that get us to quantum volume? And the answer is almost certainly, if we can pull off that coupling with reasonable rates. We can then kind of proceed down a stack. What about distillation? Distillation benefits a lot from specialized co-designs. So there's a lot of lovely work out of UMass and other folks. How do I design an IBM as well? How do I design distillation protocols given channel tomography of my noisy channel that creates these bell pairs? What if I use a memory? So there's obviously some amazing work coming out of Yale. Rob Chokov, Michel Deveray's work. They have these great dual rail or GKP qubits with very long lifetimes. If I have a 1 millisecond memory, it opens up entire new regions. If I have a 10 millisecond memory, we can actually get to the full quantum volume of our little system. And it dramatically changes the overhead required for communication. And some of the sort of earliest and most exciting places to look are actually at the algorithm side. Being able to compile more efficiently in these systems. Compilers are not well optimized to avoiding the internode link. Being able to think about distributed algorithms. Nathan Weeb in this paper highlights a really exciting development, which is distributed quantum phase estimation actually is simultaneously one of the sort of hard algorithms, quantum phase estimation, but also it sort of keeps all of its computational complexity inside the nodes. Internode, it only needs distribution of a GHZ state, which if you think way back, maybe 10 slides ago, was one of the algorithms we could already pull off with today's hardware. So I suspect that choosing the right algorithm like distributed quantum phase estimation will be important for making sure we have an early success when these systems are actually built. So I think that brings us right to time. That's the technical story I wanted to tell. Let me skip forward through some thoughts just very quickly on what this needs to happen next, and then I need to celebrate everybody who worked on this. This is obviously just one system, and it's just a very narrow analysis of superconducting systems with microwave-to-optical links. The cool thing is the analysis framework that came out of it is actually totally general. So we're repeating the same thing with microwave links. So this is more like IBM's near-term architectures. Crossbill, I believe, is the right one. Ions, neutral atoms, right? These all should be evaluated. We can also start to think about maybe distributed or hybrid systems and start to answer these questions. What if I have a hybrid memory, like a neutral atom memory connected to a superconducting system? Well, now I have this really cool memory compute separation it's with a bottleneck in between it that's very reminiscent from all of the fantastic architecture that happens inside of a classical computer between memory and compute. This is sort of a teed up question, but it's something we answered. If you have a dedicated architecture that's optimized for entanglement distillation, what does that buy you? We actually recently put out a paper answering that. It's something we're very excited about, and I can link to that later. Let me skip this and just go straight to the people. This was a huge team. It was so much fun to work with everybody. We had so many people contributing new ideas. I want to highlight in here the core team who did so much of the simulations and built the pipeline. So these are folks from PNL, from Virginia Tech, from Yale, from IBM, from Princeton, from MIT. I myself led a lot of the team and got us together to execute this project and built the architecture. So we have everybody here from experimentalists to high performance computing people to myself, a quantum systems architect. It's really been fun to work with everybody. And I think it's been my privilege to lead these folks in this project. So with that, I know I'm a couple minutes over time. I apologize, Sam. Let's go to questions.
Thank you, Michael. Nice job. Any additional questions, comments?
I have a question.
You can go ahead, please.
You said that you were looking to get faster the time it takes to do the applications or each process. So how much time were you expecting for, how much time are you looking for that the applications takes to do something?
Great.
You wanted to do faster, but how much faster?
Yeah, so we need a factor of 10 to 100. So let me pull up, wait, this guy. Let me show you the plot. So this guy here, I think this is a pretty general parameter regime. So roughly now, assuming T1 is about a millisecond, we're able to get something like 10 microseconds of gate time, maybe down to a microsecond. We really need that to be 100 nanoseconds. So at least a factor of 10 faster. And it is a little tricky because we're trading off between time and fidelity. Roughly, we need a factor of 100 total. That could be a factor of 10 times faster, a factor of 10 times higher fidelity, or it could be a factor of 100 times faster. Either one works. Getting down towards tens of nanoseconds on internode gates would be fantastic. And I don't know if there's any IBMers on the line, but it'd be fun to hear their opinion on that. We need an overall factor of 100. It can come, and at least a factor of 10 in speed. So it could come 10 in speed, 10 in error reduction, or 100 in speed, and we can reduce errors with local operations.
Okay. We have a couple of more questions. Thank you.
Great.
Vinod asked, are these systems accessible for the public?
No, they're not even built yet. So we're really mapping way out into the future here. And that's why there's so much uncertainty in our predictions. And sometimes what we want to do is, our goal here is to sort of put, I use the term a lot when we were starting this, yard lines on the grass, just to understand where does the hardware need to get so that we actually build one of these systems and it becomes accessible to the public. There are lots of single node, fantastic quantum computers accessible to the public through Google's Quantum Cloud, also on Braquette from Amazon. I highly recommend those. And when we pull this off, then hopefully you'll have a really big quantum system that is actually secretly a multi-node system that's accessible to the public.
So just to be clear, Michael, the data you presented are simulations. They are not actually performed on these multinodal superconducting system.
That's right, because nobody's built a real one yet.
Yeah.
Okay.
Okay.
There's some very small microwave link ones, but nobody's connected it up to transduction.
Okay. And we have another two-part question. Abhishek, can you maybe ask the question directly?
Yeah, for sure. Thanks, Raymond. And yeah, thank you. Yes, I was just kind of wondering on the compiler side. So how does one approach the problem of building an efficient compiler for these systems? Where in the pipeline, the compilation pipeline for standard quantum, compilation, do we need to think about that?
Yeah, so there's a number of really tricky intersecting problems here. The very first thing is you have some programmed qubits, right? You have some circuit written out. We need to assign those qubits to different nodes. That actually can rely on fairly heavily on existing classical partitioning algorithms. The tricky part then becomes in the local routing in order to actually pull computation off. I have a qubit, I'm doing some local computation with it, and it needs to get to the edge of a chip in order to be able to do an internode link. That routing is actually super expensive. There is a lovely paper out on this 3 days ago. If you send me an email, I can forward it to you. But it's both in the partitioning and then in the local operations required to actually pull off the routing required to do internode computation.
Okay. And there was a second part of the question. Do you want to ask that, Abhishek?
Yeah, sorry, it was it was basically related to the first question is what sort of properties are we looking for? And then I think Michael answered that one too. Thank you.
Okay. And maybe let me elaborate on that. I mean, the very simplest thing it needs to do is correctly trade off between extra local computation versus internode computation. And I say simplest, that's actually super hard. But it's nice to think about. And it needs to do so while still respecting sort of local connectivity constraints around that make this local computation harder and this routing harder. And it needs to, and we're developing this as a field, I think getting better and better about thinking about how to optimize between local computation and internode computation. But it needs to be able to do this sort of rapidly, heuristically, and scalably. The thing you don't want to do, for example, is to loop over all possible assignments, right? That's this massive brute force that will never scale past 20 qubits or something like that. So yeah, being able to sort of mesh these frameworks together is tricky. Something I think is still an interesting problem. And if you send me, I will send you the latest paper, which is sort of the, I think, first step forward towards a scalable solution. But if it's something you want to work on, there's very cool problems in that direction.
Awesome. Thank you so much.
Thanks. Stephen, how you doing? You want to ask your question?
Greetings. Yes, my question regards quantum volume. I was just chatting with a friend of mine yesterday about that, and we tried to nail it down for cavity quantum electrodynamics systems. Is there the IBM definition? Could you give me a really good definition for quantum volume? I
can't give you a better one than IBM, but I I mean, I heuristically think of it as in your chat, the product of qubits versus circuit depth. But I think, you know, actually being precise about it, right? It's this, you have a bunch of random 2-qubit gates on a system that's aligned in a line. And you want to be able to do both 2-qubit gates between any neighboring pair and then swap them around. And then do another random set of 2-qubit gates and then swap them around and then do another random set of 2-qubit gates. And then there's a specific metric for measuring the output, making sure there's sort of high weight. I would refer to the IBM paper on that. But yeah, so I guess heuristically, I think of it as you know, roughly width times depth. But it does have this specific mathematical formulation, and that's the one we actually use. I don't see a way to use any different mathematical formulation than the existing one.
Okay, thanks. That's a good answer.
Yeah, and yeah, let me. Have you seen the IBM paper on that? I think it's a PRA.
Yes, that's what I was referring to primarily. Yeah, we
Right,
used that
yeah.
one, but we were arguing that maybe it's the minimum of one versus the other, and we were just discussing that yesterday. So I was wondering what your take on that was.
Oh yeah, yes, yeah. So I guess like heuristically, it is qubits versus circuit depth, but there are like some super intense caveats on that. And I think that the actual PRA definition, right? This high weight output of the random SU4 circuit is what to look for.
Thanks.
Yeah.
Excellent. We have 3 minutes. Any of the last question or comment? Oh, Reed?
Yeah, I just had a quick question. So apologies if this sounds like super redundant, but it's just like it seems like the node structure, like how like I guess just like the object of is like a qubit node. It seems similar to like logical qubits, like they're currently like more studied. I guess could you quickly just like differentiate between the two? That just sort of like caught my attention like earlier on, but I just wanted
Yeah.
to, like,
So for sure, you can use nodes as logical qubits. There's good reasons to do so, and people are thinking in that direction. But the node is fundamentally something in hardware, right? It's literally a different hunk of metal with a weak connection between them. Versus a logical qubit is the way we choose to operate these systems. And so they're almost sort of at different levels in the abstraction layer, right? Like literally hardware is made in chunks, and logical qubits are sort of how we take a bunch of physical qubits and then stitch them together with some error-corrected code.
yeah.
Now, like there's cool ways to do sort of one module per logical qubit. I think it's tempting to think in that direction. There's also good reasons you wouldn't want to do it. For example, if you have 2 logical qubits that in your circuit are, have some sort of high density of 2-qubit gates between them, 2 logical qubit gates, you don't want them in separate nodes. You'd actually rather swap one in and then sort of do all of this high density region between the 2 of them, or maybe there's more than 2 of them, and then swap them out. Does that make some sense?
Yeah. That definitely clears like I guess just like the contrast of like, okay, like one's more hardware focused versus one's like I guess more of like a software approach, just like with
Exactly.
like stabilizer groups. Is it like kind of, have people thought about just like making those nodes and each one is like interlaced with like I guess logical qubits inside of them?
I don't know
Not
if there's like a
physical qubits?
specific paper on that, but it's definitely like referenced enough times.
Okay.
And so I think just to, I think something to think about that. Let me just think about surface code, because we understand the sort of gate structure and performance demands of that. For that, I need to be able to do, if I'm using this situation where a logical qubit is one module, then it's good because I have very fast intranode operations. That's very important for the actual error correction, right? I need to be able to do, I guess Google's probably what, like 1 microsecond error correction cycle. So that's very fast, that's great. Then actually putting 2 of them next to each other, the problem is if you want to do a logical operation, you need to be doing internode operations at that same rate, which becomes very steep. There's some very cool trade-offs, and if you send me an email, I will send you another paper about the sort of interaction between logical gates and error correction and seams and modular systems. Yeah, and so in that direction, it sort of becomes about doing an error correction operation across the seam. And this is specialized in the surface code.
Okay.
And that can be demanding on hardware. And so you want to minimize it somehow. And so how to interact that with some sort of compiler of logical qubits is a very interesting question. I don't know.
Okay, yeah, I guess it's like you're doing the error correction across that link, the internode link, kind of. At least sort of sounds like to me. Is that right?
Exactly. Right. And that would be like if you're doing like the lattice surgery gate, then you have to do error correction for some small amount of time, and that is steep. So then we need to be sort of understanding how many gates are we doing, how do we buffer entanglement before it, stuff like that. And there's really cool questions there that we didn't answer in this paper.
Oh, sweet. Okay. Yeah, I would love to get an email about like other papers, so I'll follow through with that. Yeah,
absolutely. My email is way back here at the beginning, when I was waxing about my route to physics. But yeah, it's in DeMarco.
Yes, Michael, wonderful presentation. Thank you all. Thanks for the wonderful discussion. I think you guys can keep going on for another 30 minutes at least, but we have come to the conclusion of this session. I don't know if is Mark still on? Mark, are you still with us?
I think he had to drop, I remember.
Okay. Yeah, but really thank Dr. Ritter for being with us, and really, the work you've presented here demonstrates the power of what C2QA is doing and contributing to the growth of this whole field. So really exciting work, and I think you were the perfect person to end the high level of enthusiasm for. Is really exciting. So I do have one last question. I know,
absolutely.
What are you going to do when you finish your postdoc?
I don't know yet. So,
are you thinking academic or industry? Where are you?
I'm interested. I know exactly what I want to do. Is I want to keep doing quantum systems architecture.
Okay.
And that can happen in national labs, that can happen in academia.
So,
I'm still searching for it. So
okay, cool. Well,
and it will hopefully be happening in companies as they scale.
Yes.
And some of the great systems architects are at Mark's company, IBM. So we'll see.
Sure, absolutely. Well, thank you all very much. Donna, Kim, are you with us?
Here's Kim.
I am with you, and I could have answered that question for you, Dr. Samuel. There is no after C2QA. It is an eternal job role for
honestly, yeah, I don't think I'll ever think differently than the way that C2QA shaped me as a scientist and this work has just been indelible, and I am so thankful for it. So.
Yeah, I think it's clearly apparent the influence of being a part of this community, how it impacts your growth and development, and I think that's
absolutely. Yeah, I mean, all 33 of these folks.
Yeah,
there we go.
I know.
Yes.
So.
And there's some other C2QAers on currently and that were on before. So I think Teague was giving the hand clap for no job after C2QA as well. So thank you.
I think Wei Tang is.
Hey guys, how y'all doing?
Yeah,
Teague and Wei were huge parts of this project, and also another one which hopefully somebody will be speaking about at one of these. On microarchitectures in heterogeneous quantum systems. So I hope you guys are doing well.
Yeah, and we also have the all hands meeting in when is that? November?
October.
October. And it's at where
is, so that is being worked out at this point, but that information will be shared probably in the next month or two.
Okay, excellent. So hopefully we'll see each other there. Okay,
great.
Excellent. Thank you.
Looking forward to it. Thank you, Ray. Thank you, Kim.
Really good meeting you all. Take care.
All right.
Thank you.
Bye.